The Quick Vision Active CNC vision measuring systems are easy to operate with advanced functionality to meet many contact and non-contact measuring needs. The unit is highly efficient and flexible, offering a wide field of view with interchangeable objective zoom lenses to meet the challenges of measuring small to large features. The 8-step zoom lens can achieve a magnification range of 0.5 times to 7 times while maintaining crisp image quality. Quick Vision Active is available with measuring ranges of 10 by 8 by 6 inches or 16 by 16 by 8 inches, with or without the
Welcome to Advanced Manufacturing Media Webinars. The topic of today's presentation is Making Sense of Non-Contact Sensors, sponsored by Mitutoyo. Hello, I'm your host, Pat Wozniak, Senior Editor of Manufacturing Engineering Magazine, which is part of SME's Advanced Manufacturing Media. Today you'll hear from Alan Sias, Vision's Product Specialist at Mitutoyo America Corporation. He'll explain the role of non-contact sensors in the industry. Our sponsor, Mitutoyo America, is a leading provider of measurement and inspection solutions, offering a complete selection of machines, sensors, systems, and services in a line encompassing CMMs, vision, form, precision tools and instruments, and metrology data management software. Mitutoyo's nationwide network of metrology centers provides application, calibration, service, repair, and educational programs for more than 6,500 metrology products. During the presentation, you can ask questions using the Q&A box that appears on the right side of the screen. Alan will answer as many of the questions as he can following the presentation. If time runs out before we answer all of your questions, responses will be emailed to you following the presentation. Another housekeeping point, as often happens when viewing videos over the internet, the quality of the presentation can be affected by the type of internet connection you have, the amount of total bandwidth available to you, and the number of people accessing that bandwidth at that time. If you experience any difficulty with the audio or the visuals of this presentation, please let us know by way of the Q&A box. If you have any other questions about any aspects of our webinars, please email me at pwozniak@sme.org. Now, here's Alan Sias of Mitutoyo.
Thank you very much, Patrick, for that introduction. I'd like to welcome everybody to this webinar. Manufacturing engineers kind enough to let us do some presentation material. In my line of work, I tend to encounter many customers that have a little bit of a fear when it comes to using non-contact type sensors, vision systems, and things like that. And part of that reason is some of the unknown is how are we obtaining data, or how is data obtained on a non-contact sensor? And so we decided to put together a presentation called Making Sense of Non-Contact Sensors, and covering some of those sensor principles, sort of looking at a cross-section of these sensors to see how we're collecting data. Now, in this presentation, we're going to cover 4 specific sensor types or methods of collecting data. There's a lot of sensors out there. There's contact sensors, there's laser scanning sensors, and other types of methods of collecting data. We're going to focus on these 4 non-contact measurement methods, namely points from focus, chromatic point sensor, tunable acoustic gradient objective, and white light interferometry. So starting with points from focus, what is points from focus? Well, we're going to see an animation here, but in general, it's allowing us to use an optic system and extend the depth of focus. So in essence, it's an optical data collection method. Okay, so if we go down a path for doing some general measurement, we would select a part, and in this case, what you see here on the bottom is an actual bone screw medical component. And above that, you see an objective lens. So we'll select a region of interest. So you can see on the bone screw, there's a region of interest highlighted that's above the threads that we're interested in measuring. And as we move the objective in the z-axis, behind this objective is a CCD camera as well. And so we're moving in the z-axis and we're capturing these images, Z1, Z2 indicated there by the frames on the right-hand side. There's many more frames in between, maybe at a slice of 3 microns, 5 microns. We're just representing 5 slices here as we move the camera in the z-axis. So we call that as an image stack. So as we move in the z-axis, we're capturing frames at a certain frequency and storing those images. And then from those images, we can actually look at each individual pixel data and build a topography, a 3-dimensional topography from 2-dimensional images. And we'll look at that in a little bit more detail on this next slide here. So if we looked at just frame Z1, which on the right-hand side is the bottom frame, the image is mostly out of focus, right? Because we're starting at a plane that's below any of the features that we can actually see on the camera. And so the result of that is a signal that's quite low on the contrast. And so some of this pixel information we wouldn't keep. We would ignore any of the pixels that were out of focus because the signal is quite low. Now, as we move to the second frame, we start seeing some of the features coming into focus. And so our contrast level meter starts getting a slight increase in its contrast. And as we move to frame 3, we can see that the edges around the thread are in focus, and so we get a much stronger signal. And this might be some information we keep for the Z heights of these pixels. Right? And then we can see that we have a high intensity on the focus portions. If we move the Z4, which is frame 4, you could see that we're actually starting to get contrast on the thread itself. And so then maybe we ignore the surrounding pixel data, but we keep data on the middle portion of this image. And then if we look at frame 5, we're again beyond the plane of focus, and so we have pretty much no contrast signal, and so we're ignoring this pixel data. And so by moving in 3D space and knowing where the frame is and knowing which pixels are in focus, we can build this topography. And so just going over kind of picking the sample part and how this works. In this case, again, we picked the bone screw and we're looking at the threads. And this might be what the field of view will look like if you had a particular camera, a certain objective magnification, and in combination, you'll get an image like this. Then, as we showed previously, you analyze each frame as you move in the z-axis and basically analyze the image stack and build a topography out of this. Now, from the topography, you could do many things. You might want to compare it to a CAD model. You might want to reverse engineer a component. In this case, we're just saying, well, let's go ahead and look at what a section of it would be. Let's select the region of interest and look at it in a 2-dimensional type profile. And so from here, then you maybe can capture radii measurements, chamfers, and some surface attributes. This is kind of becoming more and more important in the industry. Not so much I want to measure a radii or a height, but I want to see the appearance or the topography of the workpiece that I made in a little bit more detail. So any one of these regions of interest can gather many data points, upwards to 300,000. So going over some applications, what are the things that points from focus can get you? We look at the top row here. These are some sample parts. On the left side, we have our path where we showed the bone screw. Next to that is what we call a ball grid array. And those red boxes are kind of indicating the area of interest. You might have a situation with a parting line, and then over on the right-hand side, a circuit board. Maybe you're interested in seeing the leads. on the bone plate, the chamfer or the shape of the chamfer to see whether or not that bone screw is going to go in the bone plate successfully. And then things like texture. This is a knurled pattern on the right handmost side. And so as you go down in the chart, you can see, well, this is our field of view. Again, it's a combination of our magnification we're using and the type of camera. And then build a topography of that area that we're interested in measuring. And then this is here where we would actually select a section of the part to do a two-dimensional analysis. And down here is where you actually do the analysis. So you can do heights and things like that. So we're going to show you sort of how this looks in this video. Okay, so the video is not playing. So this would what you would see, what we call in the field of view. And so this is where we would move the z-axis up and down, and this image would go in and out of focus, and we could stitch those z-axes together to display and build a topography. Okay, so some of the advantages that points for focus can offer. This kind of solution that just entails an objective lens, a camera, and some analysis software, it's a pretty low-cost solution. It has relatively high throughput. As I mentioned, we can collect a lot of data, 300,000 points in data on a pretty standard CCD camera. They could be integrated into existing platforms. It has medium vertical resolution and good lateral resolution. So building a topography, you could, as I mentioned, see those parting lines or some smaller detail because of its decent lateral resolution. Limitation-wise, you can imagine if we're measuring things from pixels, then it's very sensitive to the material surface. So if it's mirrored or has a shiny surface, we no longer can see contrast, and so we can't see the information in the pixels, and we can't build a topography. And it's a little bit lower accuracy. And when we talk about limitations in this presentation, we're comparing the sensor we're discussing to all the other ones that are in this presentation. Okay, so we move on to Chromatic Point Sensor. So before I talk about the chromatic point sensor, I have to mention what is a chromatic aberration, because this sensor relies on that idea. So a chromatic aberration is a term that we use generically in the industry to describe an imaging error due to color. That's why the term chromatic is used. You can see the images on the right-hand side, particularly the bottom one. The wavelengths are actually at different focal depths due to its wavelength. Typically, we have objective lenses that are corrected for that. So, in an industry like microscopy, you don't want a bad image, right? You would have red, green, blue at shifted distances, and the image wouldn't be very clear. It would be difficult to see. So, what we are doing is using this principle. We're using the longitudinal error that the objective lens is providing us. So we're not correcting for this refractive index of the wavelengths of light. So going to what a chromatic point sensor is, and in the next slide we'll go into a little bit more detail. It's actually capturing the data, but this is just showing you its behavior. And then the next slide will show a little bit more of what's going on the inside. So again, this chromatic point sensor relies on this chromatic aberration principle, right? So the objective lens essentially is acting like a prism. It's splitting the white light up into its respective wavelengths. And then in the end, we collect data to a confocal method. Okay. So we select our workpiece. And in this case, on the left side, we have a flat type part. On the right-hand side, we have a curved surface. This is to indicate, yes, we could scan curved surfaces, and the sensor will follow the surface with feedback from the chromatic point sensor itself. And so you could select a scanning path. And so this is a little bit different than the sensor we just talked about, the PFF, in that instead of using a field of view, this actually uses a 4-micron spot size. And so we have to do a scanning path in order to collect more data points instead of defining what we called the field of view previously. So as this sensor scans of the curved surface, you can see it moves in the z-axis to follow and track the z, as well as move in radial patterns, and we're collecting data point by point at some frequency in the x, y, and z, which essentially allows us to, once again, pass this data to a spectrometer. And again, next slide we'll go into a little bit more detail how this works. But it goes to a spectrometer, and from there we can actually determine the topography. Very similar to the previous one, but we'll go over advantages and limitations a little bit down the road here. So on the inside of the chromatic point sensor, what is happening? Well, we have a white light source that is actually going through this objective that we described using that longitudinal aberration property. And so each point that's in focus is different for each wavelength. So if you can see the graphic there, we have red, green, blue sort of split up, and green is hitting the workpiece where red and blue are not. And so what will happen is any light waves that do not hit the workpiece end up not passing through this pinhole. So you'll see here we have a pinhole, and this is where the confocal method comes in. Any ray of light or wavelength that is focused on the workpiece surface will go through that pinhole. And so thus, it will end up hitting the spectrometer after the pinhole, and we can actually see the wavelengths along that spectrometer. So essentially, we end up using the spectrometer like a ruler. It's just measuring the wavelength peak shifts, and then we can actually determine the heights from the wavelengths that went through the pinhole. So some application examples here. We have a thickness measurement of some translucent material. We can actually take the CPS, scan it, see the top and bottom simultaneously, and measure an upper and a lower surface. On the right-hand side, we also have a lens array where we could scan in a serpentine type pattern and get a result that you see there for some 3D analysis, maybe measure the spheres of the lens. So some of the advantages from chromatic point sensor. As we sort of talked about, it can measure translucent surfaces. Because of that chromatic aberration property, we can see maybe red coming back at some angle and green coming back at some angle at the top and bottom of this translucent material. But that doesn't mean we can't measure diffuse surfaces. So we can measure translucent and diffuse surfaces with this type of sensor. It does very steep inclined surfaces up to 80 degrees, heights and depths. This type of sensor allows you to actually adjust the intensity because you get some feedback from it. So let's say you went from clear material to a chrome type material. The intensity would adjust automatically to get rid of any kind of noise you might see. It's very high accuracy. Some of the limitations, we did mention small spot size diameter. It's a 4 micron spot size, pretty tiny, hard to cover large workpieces, and it's a little bit slower, so we end up with lower throughput. Next topic is the tunable acoustic gradient objective. So what is a tunable objective? So if you're not familiar with a tunable objective, let's talk about what we are familiar with. Standard lenses, right? If you have binoculars or something, these are solid glass lenses. You might have some moving components to change the optical path slightly so you could see further, bring things into focus. And this is much like the human eye. Depending on where we're looking, our cornea actually will reshape itself so that we are modifying the wavefront so that the images that we see are in focus. So tunable means we have the ability to change the wavefront of an objective lens. And there's a lot of different ways to do this. There's mechanical methods, optical methods, which a lot of us are familiar with, zoom lenses and things like that. There's thermal type of tunable lenses and electrical. In this example, though, we're actually showing an example where we're using liquid inside this objective lens. And so, how do we do this? Well, basically, you have a silicon oil type material inside the objective lens, and you pass sound waves into it, and you can actually modify the wavefront. Well, because it's controlled uniformly, and this type of liquid actually creates these density variations, we're actually controlling the refraction of index at very high speed. So you can see there 70 kilohertz to over 1,000 kilohertz. And in the end, what you end up with is a very large extended depth of field. So if we go back to what points from focus showed us, we could build an image stack by looking at slices at different levels by moving in the z-axis. This one is actually doing it at the objective side, so we essentially do not need to move the z-axis. That allows us also to capture this volumetric information and produce measurements. So just to clarify, how that works. So in a standard system, right, we have 3 optical paths shown here on the left-hand side of that diagram, where the lens element is moving. So this is essentially simulating like a zoom lens setup. And if we look at the top one, the leftmost image, and between those 2 black lines, we'll call this our depth of focus, the DOF of this optical configuration. And so only this region will be in focus. If we look at the middle one, we can see we have a different location that's in focus, but still the depth of focus did not change, right? And then on the bottom, we could yet get another plane that's in focus, yet again, the depth of focus does not change. So what the tag lens actually allows us to do is it's integrated into the existing system. There's no moving parts, so we're using sound and liquid again. And now all of a sudden our DOF is from the beginning of where the zoom lens capability was to the end of where the zoom lens capability was. And everything in between is all in focus. So we're getting all the data instantaneously and simultaneously within this optical path here. So just to kind of go over that again a little bit differently. So we have, in this case, a 35 millimeter camera. We have an intensity chart here, and then a Z location of what the depth of focus would be. So we indicated here with this DOF 8 millimeters. But a tag-enabled system, depending on the intensity of the illumination here, we're getting a depth of focus of 800 millimeters. And you could even improve that a little bit further by introducing a light-aided system. So what does that mean? Well, you can synchronize the pulsed illumination system when you're capturing the frames at that very high rate that we've discussed. And essentially, in that 800 depth of focus range, it's important that you have a lot of pixels at a higher intensity, because as you move up and down to the plane that you're trying to measure, you don't want to lose any information. So the light-aided system gives you a higher intensity pixel data over the 800 millimeter depth of focus. So going over another example here, where we're using that pulsed illumination and timing it based on the frame rate of the camera. We have a 20 euro cent in this setup and a 5 euro banknote, where the 20 euro cent is set up at 300 millimeters and the banknote is at 850 millimeters. So this camera that we're using here, its native depth of focus is 44 millimeters. So if you look at that graph below, that blue square is indicating the camera's depth of focus. And the orange square is indicating what we're currently looking at. Right? So right now, the tag tunable acoustic gradient is not functioning right now. We're just looking at what the native camera is letting us see. So in this second image, you can see that we're only focused on the banknote. And we no longer can see the coin. The coin's out of focus, right? And because we're still on that, our native depth of focus of 44 millimeters. But once we synchronize our camera with the pulsed illumination, we could see both the coin and the bill simultaneously, where we're essentially extending the depth of field in this scenario to 550 millimeters, which gives us a result of about 12.5 times the native DOF of the initial setup. And again, all this is a component that's being placed within the optical path. There's no other items besides this and a sound generator. With some feedback information, of course, but as far as the optical system goes, there was no modifications. So some examples here is we talked about some volumetric type analysis. So and on the left-hand side, we have some life science applications here where they're actually looking at the red and white blood cell flow in a capillary of a live mouse. And on the right-hand side, this image you see is, or video is calcium imaging in response to visual stimuli. So again, both of them showing volumetric type analysis. So some of the advantages of a tunable acoustic gradient. As I just mentioned, volumetric analysis, so you could see X, Y, and Z. We have a very large extended depth of focus. High speed, there's no moving parts. It can provide positioning feedback. No need to focus or scan in the Z-axis. So this could be important if you were designing a machine expecting to have a Z-axis, a motor, a counterbalance, and a scale. You can reduce weight and cost by implementing something like a tunable acoustic without having the need to move in the Z-axis. Simple integration, as I mentioned, this was just placed pretty much in the optical path at a certain position. So there's no changes to your current optics required. And then some of the limitations, being camera speed and the intensity of the illumination. As we mentioned, we're pulsing light, and so if you pulse light and it's more intense, you could actually increase your capability of the pixels that you're getting back to the camera. And then the faster you can do that, the more planes and levels you can see within that gradient. So this moves on to white light interferometry. So I do have to back up a little bit and talk about what light wave interference, because this is white light interferometry relies on this light wave interference principle. And so waves in general, whether they be on water or electromagnetic in nature, when they overlap or come into contact with each other, they're going to have some influence on one another. So just as an example, what we call these two are synchronous waves, right? So the top one and the bottom one, above and below the plus symbol, are identical. And so what happens when you add these waves together, the amplitude basically doubles because they're what we call constructive interference. So it's the sum of the waves, right? And then you have something where we can go to completely zero, where if we offset the wave, the second one here, you can see it's been shifted by half the wavelength. And the amplitude basically goes to zero because this is complete destructive interference of whatever waves we're discussing here. And then finally, there's something that happens in between. You don't always get waves that are synchronous or offset by half the wavelength. But as waves interfere, you might get some different interference patterns. So again, white light interferometry relies on these interfering waves. And if you look on the right-hand side, we have some interference patterns that are actually projected onto our CCD camera. And so an interference projected to the CCD camera, so we represent these, the CCD camera by these squares here, where the red one indicated that it picked up some interference pattern. Okay, and that's important because, well, whenever we see an interference pattern, this basically lets us know that the part is in focus. And so we get an interference pattern on the pixels, and again, we're talking about pixels. We're trying to gather some information from the interference pattern that's hitting the CCD array. And similar to the other methods, as we move on the z-axis, the interference fringe patterns will change, and then we can build a topography. So here's sort of what the optical path will look like. You have a white light source, and this white light hits the beam splitter, going down to what we call the interference objective lens, which then passes through the beam splitter and bounces off the beam splitter to the reference mirror. So all of the illumination that actually ends up hitting what we call the measurement target goes back up through the beam splitter and starts interfering with the light coming off the reference mirror. And then this image ends up getting passed to the CCD camera, and so because the reference mirror and the measurement workpiece are interfering, you get an interfering fringe pattern, and this whole optical path could be contained maybe in a z-axis or something like that, which we'll sort of show here. So when we go through the animations here, you'll see a red dotted line that's indicating the focal point of the CCD camera, and then we'll move upwards in the z-axis to capture pixel information. So there's the red dotted line. Again, these little squares representing our CCD array. On the right-hand side, you have the white light interferometer image. And any blue squares you see are indicating, okay, well, these are pixel data information that we want to look at and we keep. So as we move in the z-axis, we have a different focal point, and we have a different signal on a CCD array, and we're capturing a different WLI image. And then we move to the top. And so as we're picking up more and more slices and more interference patterns, we can combine all this information into doing a 3D shape analysis. And again, we can slice this two-dimensionally, compare it to CAD, or even reverse engineer. So an application example here might be like a microcircuit, right? So we have, again, a region of interest. You know, to the right of that, we could define a scan area, maybe a serpentine pattern inside this red box with a margin of a certain distance. That's the yellow area here. And then on the bottom, you know, getting a trace or a set of data like this, and we could slice it down the middle and look at the heights and widths of this microcircuit. So some of the advantages of WLI. It performs very high aspect ratio measurements. So let's say we had a 10 micron width and a 10 micron height on a very small type of part. This type of sensor could do that, whereas something like the Chromatic Point Sensor would not be able to do high aspect ratio type measurements. This is high accuracy type of measurements. It can do very small, minute form measurements. So if you're looking for very small planes, small lands, and things like that, this sensor could do that. It even has the potential to do non-contact surface roughness because of its nanometer level resolution. And then some of the limitations, it has a quite small working distance typically, and it's a little bit slower than the other sensors we were discussing. So as you get closer to the workpiece, then it limits you to a little bit of what you can measure, because if the workpiece is tall and you need to measure something that's deeper inside the part, you might not be able to use this type of sensor. And so then, to finalize the presentation here, this is just sort of a chart that's comparing all these sensors side by side. And so you can see things like the z-axis resolution of the actual sensor itself, where point from focus is 50 to 100 nanometer range. And then you can see CPS is 25 nanometers, and then tag being 2 to 3 microns, and WLI being 1 to 10 nanometers. So, as we mentioned, WLI being very high accuracy, however, the throughput is much lower. So you always have this trade-off between whether or not you're collecting a lot of data very quickly and how accurate it is, and what your throughput result is. So the higher your throughput, typically your accuracy starts going a little bit down and your resolution suffers a little bit from that. Okay. And then below there are some applications. So PFF could do things like that bone screw we saw, and the ones we listed there, some diamond chips and microvia, where the CPS is great on transparent material, so you could do glass and lens arrays and things like that. For tag, it has a little bit more besides life science, so we could use it in the packaging industry, or maybe seeing very far with some drone technology. As we mentioned, volume imaging or security or even QR code reading. And then for the WLI side, IC packages and solar cell surface properties and other things like that. So I'd like to turn this back over to Patrick, and we can go over some of the question and answer session.
Hi, this is Pat Wozniak joining you again. Thank you, Alan, for a thought-provoking presentation, one that has generated some questions. You mentioned other types of sensors. What did you mean?
So we covered, we covered WLI, points for focus. There's other sensors out there than the ones we described here, and of course, they're going to have their own types of principles along with them, but there's laser type scanning on platforms that are out there. There's even radar now for doing macro type measurements. So that's what I meant by just isolating these four and comparing them to each other. However, there is other non-contact methods out there.
I see you can measure the surface with the sensors you mentioned. Can these sensors measure features below the surface, Alan?
Yeah, so you're going to have a different types of parts you're going to measure. If you had a through hole, we could avoid the through hole. If you had a blind hole, let's say, you should be able to measure the depth of the hole. Some of these sensors won't be able to measure all the way down into the blind hole, depending on how low how deep the hole is. But yes, you can measure below the surface. But if there's features on the underside of the part, obviously it would be something that we can't do. The part would have to be flipped over to see those features. Unless you're using something like the chromatic point sensor, then you can see through translucent type materials, where you can measure the top and bottom simultaneously.
What type of platforms can you integrate these sensors into?
Well, typically in our industry, these are non-contact sensors, so they can go on vision platforms. But the purpose of the webinar and the presentation is to say, well, we could put these on most any platform and integrate into other things. The idea here is to show, let's get a lot of data. Here's a data collection method, and we can do some analysis using some powerful software.
It seems like you show field of view with PFF. Can you measure multiple fields of view?
Yeah, so our example of PFF, points from focus, showed one field of view collecting around maybe 300,000 data points or less. You can definitely stitch images for any of these sensors that we discussed in the X and Y. And so, yes, we are stitching things together in the Z to build topography, but you can also add in X and Y and do one field of view at a time and then decide what your stitching overlap would be. And you can do many field of views if your workpiece is larger and needed to have a ton of data on the topography.
Unfortunately, our time is running short. We'd like to thank Alan Sias of Mitutoyo for sharing his time and knowledge with us. And we'd like to thank you, our listeners, for joining us as well. All unanswered questions will be passed along to Mitutoyo, and you can expect a reply via email. Also, the entire webinar will be available for replay by 4 p.m. Eastern Time today, and you can access it by using the same sign-in link you used earlier. As this webinar has shown, manufacturing is getting smarter. A new magazine produced by SME, Smart Manufacturing, was launched in May to help educate manufacturing professionals about the new and emerging technologies used to make things in this digitally connected new era known as the Fourth Industrial Revolution or Industry 4.0. IoT, of course, is a big focus of smart manufacturing. Readers can find that first issue and the second one at www.sme.org/smart and learn how to subscribe to this new publication. Advanced Manufacturing Media delivers the latest manufacturing news at our improved and revamped website, www.advancedmanufacturing.org. And finally, if you'd like an in-person look at the latest in manufacturing trends and technology, SME will make them available at FabTech, November 16th through 18th in Las Vegas, HughesTex, which is in February 28th through March 2nd next year in Houston, and also at AeroDev, March 7th through 8th in Fort Worth. Thanks for joining us for this Advanced Manufacturing Media webinar. We hope you found it informative.